So question 8 is saying the displacement of a particle in the x. Let me just put in the x. Okay, so the displacement of a particle in the x-axis depends on the acceleration and time t. The displacement of a particle in the x-axis depends on acceleration and the time t. Derive the relationship between x, which is the displacement, acceleration a, and the t. The displacement of a particle in x-axis depends on the acceleration and the time t. Derive the relationship between a, which is acceleration, x, which is the displacement, and t, which is time in this case. So how are we going to approach this question? So there are actually two ways in which you can solve this question. If you want, those who have taken pures before at secondary school, you are supposed to use calculus. I'm sure you already know what calculus is. You're supposed to use calculus where you start differentiating acceleration. You know, to say acceleration is the differentiation of velocity over the differentiation of time. Then you start moving. In that case, you are solving for you, or you just follow that process. You differentiate, you integrate, and so on and so forth. But for me, who has been looking at these formulas for quite some time, I already know the relationship that they are looking for. I already know the equation that relates displacement with acceleration and the time. So in short, I can just give you that equation, and if you write that equation, no one should mark you wrong because it's the correct thing, because it's giving the relationship between acceleration, displacement, and time. It's just that I'm not going that calculus way where we're supposed to differentiate then we start integrating everything to come up with the equation. We can just go straight to the point. So this is question 8. Okay, so this is question 8, and they've given us x, which is displacement, and displacement is distance, so it is in meters. We have acceleration. Acceleration has units, meters per second squared. Then what else have we been given? We've been given time t, which will be in seconds like this. And for this case, since they didn't specify, we're going to consider the initial velocity of this guy, the u, as 0, since they didn't give any specification. So we're going to use the equations that we already know. As I've already said, I'm not going to start deriving the equation just now, unless they tell me they want it in that route. But this question is actually very simple, so we can just do this. We're going to use the kinematic equations that we already know. The second equation of motion, which is relating all these three that we've talked about, where we have displacement, we have acceleration, and we also have time and the initial velocity. So which equation is that? See this guy. Displacement is equal to initial velocity multiplied by time plus half, which half is a constant here, multiplied by a, of which a is acceleration in this case, multiplied by t squared like this. So we've said they didn't specify about the initial velocity, so we're going to assume that our initial velocity is actually equal to 0. And if we plug it into this guy, we're going to get x is equal to what? X is equal to half a t squared. Why? It's because the 0 that is on the initial velocity is taken out this part of our equation. Now we can check out the dimensions on both sides to see if the relationship that we've used is actually working. You know, to say x is in meters, that means we have meters on the left hand side, and this is supposed to be equal to what? It's supposed to be equal to acceleration multiplied by time squared. We're not including the coefficient or the constant half, because this is dimension analysis and we are not supposed to focus on constants. So m, which is meters on the left hand side, should be equal to acceleration. We said acceleration is equal to meters per second squared multiplied by time squared, which means this is second squared like this. So this and this is going to cancel out, such that we're remaining with what? We're remaining with meters on the left being equal to what? Being equal to meters on the right. Hence, we're going to conclude to say the equation that relates x, a, and t is equal to what? It's this guy that we had here. So we're going to say x is equal to half a t squared as the equation which is giving us the relationship between displacement, acceleration, and time. And that is all on question 8. Okay, now move on to the next one, which is question 9. Also, somehow looking a bit complicated. Question 9 is saying a physical quantity x is related to 4 measurable quantities A, B, C, and D as follows. X is equal to a squared, b to the power 3, open bracket, the square root of c, close bracket, to the power 5, divided by d squared. Given that the percentage errors in the measurements of the quantities A, B, C, and D are 1%, 2%, 3%, and 4% respective, what is the percentage error in the quantity X? If the value of X calculated on the basis of the above relation is 2.76312, to what value should you round off the result? We read the question again. Given that the percentage errors in the measurements of the quantities A, B, C, and D are 1, 2, 3, and 4% respectively, what is the percentage error in quantity X? If the value of X calculated on the basis of the above relation is 2.76312, to what value should you round off the result? So this is question 9. Okay, so what are we going to do here? We're supposed to find the percentage error in X. This is the first thing that we're supposed to do. So question 9. Question 9. First thing is we're supposed to calculate the percentage error in X. So what are we going to notice? The percentage error that is going to be in X is or in this quantity that is derived using this formula is going to be found by adding all the relative errors that are contributing to the percentage error of each variable. And how are we going to do that is by considering their exponents. If you look at the formula that they gave us a formula that had the exponents on the quantities that they gave us. To say we have A was squared, we have B is to the power 3, then you have open brackets, you have the square root of C, then you have to the power 5 here, then you have what? D squared like this. So the percentage error in this or in a quantity that is going to be derived using this formula or from this formula is going to be found by adding the relative contributions of the percentage errors of each of these quantities or each of these variables that I've written here in this equation. And how are we going to do that? By considering their variables. So on B there's power 3 there, by considering their powers, not variables rather. by considering their powers, or sometimes you can just call them exponents. Okay, so this is the formula that we have, and the percentages for contributions we have A, B, C, and D. We've heard to say A is contributing how much? A is contributing 1, 2 here, 3, and 4. A is contributing 1%, B is contributing 2%, 3, or C is contributing 3%, whilst D is contributing how much? 4%, like this. So now that we have these guys, and we've said we're going to find the summation of all the errors that are contributed by the quantities that are in this guy, considering their exponents, what are we going to do? The percentage error of x, or the percentage error in x, is going to be found by multiplying each contribution of these quantities in the percentage error by the exponent of that quantity. I hope that is clear. So from a squared, since a is squared, what are we going to get from a? I want to say this multiplied by 2. 2 is the power there. From b is to the power 3. So what are we going to do? We're going to multiply this, the 2% multiplied by 3. Since c has the, or c is written in this form, so c is like this. There's c here, then there's power 5 like this. What are we going to do? I want to notice that this square root here is the same as we have what? We have 1 over 2. Or we have c to the power what? C to the power 1 over 2. And since there's another power here outside, what are we going to do? Oh, let me do this. We have c to the power 1 over 2. And this guy is in brackets, and we have another power 5. So what are we going to do to the powers here? We're going to multiply these powers. We're going to say half multiplied by 5. Hence, we're going to come up with the conclusion that the power of c is what? The power of c is going to be equal to 5 over 2, which is the same as 2.5. So I'm going to multiply this c here by 2.5, which is the power of 2. Then d is a denominator, but it's also contributing in the same manner. So what are we going to do? We're also going to multiply it by its power. So this multiplied by 2 again. I can rub this side. Okay, I can rub here. So from these guys, what are we getting? We have 2% here, which means the maximum contribution of A is 2%. The maximum contribution of B is 2 multiplied by 3, which will be 6%. We have the contribution of C, which is 3% multiplied by 2.5, and this is going to give us a maximum contribution, or a total contribution of C of 7.5%. Then we have D, which is contributing 4%, and we are going to multiply it by its power to get the total contribution of D to the percentage uncertainty of 80%. So these guys have said they are contributing equally into the percentage error of X. So what are we going to do? In order for us to find the percentage error in X, we're just going to add these values, the total contributions that we found here. And how we're going to do that? We're going to say 2% plus 6% plus 7.5% plus 80%. And that is going to give us the total percentage error in X. So I'll write here total percentage error. Total percentage error in X will be equal to 2 plus 6 plus 7.5 plus 8, which is going to give us a total percentage error of 23.5%, which means X has a percentage error of 23.5%. And that's that. We found the percentage error in X. As simple as that. So you should just master how you're supposed to approach such a question, because in your exam, they won't give you exactly this, but they might bring something that is just similar to this or closely related to this. And just because they put where there's a 2, they put a 1, where there's a power 3, they put a power 6, that shouldn't confuse you. The approach is the same. Okay, so that is the total percentage error in X, and the the next question was saying, since the actual calculated value is 2.76312, to what value should you round off the result? To what value should you round off your result? Okay, so we're going to use this same calculated value of X that they've given us to say this is equal to 2.76312. This is the value that they've given us. So we found the percentage error of this to be 23.5%. So what are we going to do first before we find to how much we rounded off? We're going to find the absolute error of this guy. And how are we going to find the absolute error? Is by multiplying the percentage of this by this guy. So what are we going to do? We're going to divide this by 100. We know how to multiply by percentages. So divide this 23.5% by 100 to get 0.235, and we're going to multiply this guy to 2.76312. So I'll say my absolute error. I'm finding my absolute error. My absolute error will be equal to 23.5 divided by 100, which will be equal to 0.235 multiplied by the actual measured value of X, which is 2.76312, like this. So how much is the absolute value? I'm going to get 0.64933. This guy. So this is the absolute value from the measured value of X that they've given us. So the result now, the final result, should be rounded off to a number of significant figures that is actually reflecting the uncertainty. And the absolute error we found to say it's this one, which is suggesting that we should round off to one significant figure in the error, which is corresponding to the first uncertainty digit in X here. This is the value of X that we've measured. So we're supposed to round this guy to a value of 1. And if we round off, or if we check this absolute value that we found, you're going to find that this absolute value that we found is greater than 0.1. You can see it's 0.64. It's greater than 0.1, but it's less than 1. What does that mean? That means we should round off X to 1 decimal place. I hope you've heard the explanation. The absolute value that we found is greater than 0.1, but it's less than 1. What does that mean? That means we should round off the value of X to 1 decimal place, which is going to give us the actual value of X of what? Of 2. Since 6 here is greater than 5, we're going to say 8. The value of X is 2.8. Hence, we found both the questions that are in question 9. Here the explanation on the second part here, it is the one that is leading us to the actual answer to as of how much decimal places we should round off the value of X to. So that is all on question 1 or on question 9, guys. We can now move on to the next question, which is our question 10. Question 10 is saying a lab test result for hemoglobin is 13.2 grams per deciliter, and the non-standard is 13.0 grams per deciliter. A, what is the absolute error? B, what is the relative error? So these are the things that we already talked about on Saturday. how to calculate absolute error, how to calculate relative error, how to calculate absolute uncertainty, and also relative uncertainty, of which sometimes relative uncertainty is just finalized to percentage uncertainty, or relative uncertainty being also known as fractional uncertainty, which can be actually completed by just multiplying it by 100 to find the percentage uncertainty. So they've given us these two values to say we have 13.2 as the lab test result. Question 10. Question 10, they've given us 13.2 grams per deciliter. 13.2 grams per deciliter. This is the measured, and we have the non-standard to be 13.0 grams per deciliter like this. So they've asked us to find the absolute error. And how do we calculate absolute error? Absolute error is just the difference between the measured value and the true value. We already defined this. So absolute error, I'll be writing in short forms. You can complete it in your assignment. This will be equal to what? Will be equal to the measured value, the absolute value of measured value, of which I can just call this MV. Measured value minus the true value like this, which this will be equal to what? This will be equal to 13.2 minus 13, or 13.0 like this. So that means our absolute error will be equal to what? Will be equal to 0.2 grams per deciliter. So our absolute error is 0.2 grams per deciliter. From here, what are we going to do? We're supposed to find the relative error. From here, we're now supposed to find the relative error. And how do we calculate relative error? Anyone who attended the class? Relative error, lady, that's equal to absolute error over the measured value multiplied by what? Multiplied by 100. Multiplied by 100. So this is what we are going to do. The relative error will be equal to what? It will be equal to absolute error minus, or over true value. True value, this multiplied by 100%. And this is going to be equal to what? This will be equal to 0.2, which is the absolute error, over the true value, which is 13. Multiply this by 100%. And we're going to get a relative error, which is equal to 1.54%. The relative error in our calculation is 1.54%, and that is the final answer. So the absolute error is 0.2 grams per deciliter, whilst the relative error is 1.54%. That is all on question 10. Question 11. Question 11 is saying a nurse weighs a patient 3 times and records 59.5 kilograms, 60 kilograms, and 60.5 kilograms. Calculate A, the mean weight, B, the estimated uncertainty. A nurse weighs a patient 3 times and records 59.5 kilograms, 60.0 kilograms, and 60.5 kilograms. Calculate A, mean weight, and B, the estimated uncertainty. Okay, so what are we going to do here? This class is now getting a bit tiresome. I think I've talked a lot alone. Question 11. They've told us to say a nurse has measured the mass of a patient 3 times. So she has gotten 59.5, 60.0, and 60.5. All of these are in what units? In kilogram. So question A is saying calculate the mean weight. And how do we calculate the mean weight? We're just going to add the three figures that we've been given divided by the total number of figures. So our figure is 3 in this case. So we'll find the mean weight. We're going to say 59.5 plus 60.0 plus 60.5. These are in kilograms divided by the number of figures that we have, or the number of measurements that we have, which in this case is equal to what? Is equal to 3. This is going to give us how much? This is going to give us 180 over 3. And this is going to give us a mean weight of 60 kilograms. But that means the mean weight here is 60 kilograms. And the next question, which is part B, is saying estimate, or what is the estimated uncertainty? Find the estimated uncertainty. So the uncertainty here can actually be estimated using the range. What do we mean the range? It's the difference between the maximum number, which is 60.5 here, and the minimum number, which is 59.5, divided by 2, as a simple approximation for multiple measurements. So what are we going to do to find the estimated uncertainty? We're going to say estimated uncertainty would be equal to the difference, or the range. What is the range? The range is the difference between the maximum number, which is 60.5, and the minimum number, which is 59.5, like that, divided by 2. So I'm going to say 60.5 minus 59.5 divided by 2, like that. And what's the actual difference between 60.5 and 59.5? This is equal to 1. And 1 divided by 2 are going to get an estimated uncertainty of how much? Of 0.5 kilograms. The estimated uncertainty is actually 0.5 kilograms. Okay, and we can see to say from our mean weight, we can add 0.5 to get the maximum number, which is 60.5, and the 59, subtract 0.5 from 60.0 to get 59.5. That means if we want to write this number correctly, or want to write our weight of this patient correctly, we can just say the weight is equal to what? It's equal to 60 plus or minus 0.5 kilograms, like this. Because if we add this 0.5, it is going to give us this guy. If we subtract this 0.5, it is going to give us this guy. And that is all on question 10. Found the mean and also found the estimated uncertainty. Or that is all on question 11, sorry. We'll move on to the next one, which is question 12. Question 12 is saying the radius of a circle is measured to be 10.5 plus or minus 0.2 meters. Calculate A, the area, and B, the circumference of the circle, and give the uncertainty in each value. The radius of a circle is measured to be 10.5 plus or minus 0.2 meters. Calculate A, the area, and B, the circumference of a circle, and give the uncertainty in each value. Okay, so what are we going to do here? This is the second last question, which is our question 12. Question 12. The they've told us to say the radius r is equal to what? Is equal to 10.5 meters. Then there is uncertainty, which I can label as uncertainty in r, which is equal to what? Which is equal to 0.2 meters, like this. So we want to calculate the area and the circumference of this circle. So the formula for area is equal to what? Area is equal to pi r squared, like that. And what about circumference? Circumference is equal to 2 pi r, like that. So the uncertainty now, that's where a bit of an issue is. In order for us to calculate the uncertainty in these two quantities that we're going to solve for, the area and the circumference, what are we supposed to do? We're supposed to take note that to find to find uncertainty in a function that looks like this, of which in this case we can say we have an example of a function which is equal to k r to the power n. What do we do, or the relative uncertainty? How do we calculate the relative uncertainty of this guy? So we use this formula to say the relative uncertainty of this function can be equal to what? Can be equal to n, of which n is the power here, multiplied by what? Multiplied by the uncertainty in r, which is here, like this. So this is the formula that we are supposed to use in order for us to find the uncertainty in such functions as these that we've been given here. So what am I going to do? I'm going to plug in to find my area. So area is equal to what? Area is equal to pi multiplied by 10.5 squared. So area is going to be equal to what? Area is going to be equal to 346.36 meters squared. Square meters, like this. And what about the circumference? Circumference, you can say this is equal to 2 multiplied by pi. The way it is pi, just punch it on a calculator, multiplied by your radius, which is 10.5, like this. And we're going to get circumference, which is equal to 65.97 meters. Yes, the circumference is 65.97 meters. So using this function that we've dropped here, are we able to calculate the uncertainty in both A and area and circumference? Yes, we can. I'm just going to plug the values that you already know into this function here, or this equation here, to get the uncertainties in both the area and the circumference. So I'll put this down here. So for area, for uncertainty in area, using this function, we are going to say this is going to be equal to what? We know to say n in the formula for area, n here, which is this guy, is equal to 2. So we're going to plug this 2 where there's n here. And we are looking for uncertainty in area. So I'll change also here and put area, like that. Then we have our radius, just like that. So we're going to plug in what we know into this formula. So we have 2 here. Then we have uncertainty in radius. We already have the uncertainty in radius. So that means we're going to say uncertainty in area will be equal to 2 multiplied by 0.2, which is uncertainty in radius, divided by the actual magnitude of our radius, which is 10.5, like this. Okay, and from here, we can actually multiply. If you multiply, or if you divide 0.2 into 2, or 10.5 into 0.2, what answer are we going to get? Anyone with an idea, or anyone who has a calculator? closer to them. Anyone who has a calculator closer to them? Remember, this A is just the actual area, so we can also plug it in. And we found actual area to be 346. 346.36 like this. So we can just plug it in there and find the answer. So when I plug this, I'm getting an answer which is equal to uncertainty in A is equal to, here, this side, when I plug this in, I'm getting 0.0381, and I'll multiply this by the area, which is the denominator there, which is 346.36. Yes, I'm getting an uncertainty in my area, which is equal to what? Which is equal to 13.2 square meters. 13.2 square meters as my uncertainty in area. As simple as that, I can also go to the circumference. The same formula, we're going to say uncertainty in circumference over the actual circumference is equal to n multiplied by uncertainty in radius over radius. So since n here on this equation for circumference is equal to 1, the power of r here is equal to 1, we're just going to put 1 here. So we're going to say the uncertainty C over the actual C over the actual C will be equal to 1 multiplied by 0.2 over 10.5 like this. Okay, so get this side, I'll multiply it. Now I'm going to remain with uncertainty in C to be equal to 65 or 65.97, which is the circumference, multiplied by 0.01905, giving us the uncertainty of what? 1.26 meters. Okay, so that is the uncertainty in our circumference, just like that. And our uncertainty in area is 13.2, just like that.